Hello everyone, this is Kaveh from Honolulu with lesson 12 of our Common Lisp animation and OpenGL tutorials. So we're going to continue a little bit with animation and start playing with hierarchies and animations, which is a lot of fun. So a few utility functions first. We define a function tween, which takes a value and a start point and a start value and an end value, and returns a value between 0 and 1. That's the interpolation, or the interpolated value between those things. So basically, if it's less than start, it's 0. If it's greater than end, it's 1. Anything in between, it's between 0 and 1 as an interpolation of those. And then we have an interpolating point function that takes a factor between 0 and 1 and return between 2 points and returns an interpolated point between those two endpoints. And we have a number version of it as well, which does the same thing for numbers. Then we want to do a smooth interpolation between points. So we'll see a little bit later what we mean by that. But we use a cubic function, which has an S shape and gives us a smooth value between 0 and 1, which is flatter in derivative around at the endpoints. So let's just compile these. All right. Now, I'm going to introduce a new concept in Common Lisp, which is basically A-lists or association lists. Sort of a very simplified version of hash maps, and probably not as used anymore now that we have proper hash maps. But basically, we have lists of values, keywords and values, and we can basically get, set, and add keywords and values in them very simply. So I'm just going to, let me just quickly compile the get value, add value, and set value. So here we have what an association list might look like. So key is foo and the value is 1, key is bar, the value is 2, the key is baz, the value is a string, hi there. And the dot just means that it's a cons and not a proper list. That's something that you should be aware of as you work on with lists in Lisp, that not every list is a proper list, it has a nil as its last cooter. But let's not get bogged down in those details. So we define my A list. So if we look at it now, oops. So it simply echoes out what we have here before. Now, if we want to get a value, we call the get value of the A list, and the value for bar is 2. And if we want to set the value, we call the set A list value. So we can see that foo got a value of 99. But if we look at so we can the value of our actual parameter or variable, we'll see that it did get updated. So this is a destructive operation. It's a destructive operation because that's the way we wrote it in our setter function. And then we can get the value of another thing, which is, so this basically, since we don't have this key, QUX, in the list, it simply returns nil silently. If we try to set it, it's going to return an error message. So we get an error message. And we quit out of it because we can't set a key that doesn't exist. If we define the semantics differently, that would automatically add the key, but we're not doing that. So what we can do instead is basically we can add the value for that key. And this is not a destructive operation, so basically we have to set our A list to be that new value. And if we look at the new value of the A list now, we can see that the new key QUX is there. So the reason we're doing all this is basically it's a quick and easy way for us to store values within our animators. So far the animators haven't stored their own data, but we're going to let them do that now. So we're going to basically add a data slot to our animators, and we want to get the anim data. It gets it as an A-list value. So the data is going to be an A-list association list in the animator. We can put values in there, and then the animators init and update functions can then get those values as they need to. So let's see how that might work. We define our hexagons as usual, and before we had them rotating by random amounts, but we were defining the random amount outside and then passing it to the animator and using the lexical closure over the update function. So what we're going to do now is basically have a data that contains a rotate value, and it gets a random value between 0 and 5 to start with. And this gets assigned to every leaf node. Oops. Oh, I haven't compiled these forms. So we got that guy. So now if I go in here and I hit the spacebar, we have our rotations between 0 and 5. And what it's doing is basically the update function is calling the rotate by the anim data for that instance of the animator. And if we do a similar thing here now with our grid of squares, if you remember before with the grid of squares, we couldn't really have an init function the way it was set up, because if you set the initialization to be 0 for the translate, everything goes to the origin. But here, as we traverse the hierarchy, we store the start position, oops, pardon me, wrong key. We store the start position of each of the transforms of our leaf nodes, and then when we create the animator, the initialization function will translate to that start position, whereas the update function will translate by, again, some random value that we had before. Let's increase this so it's more noticeable. So what that does for us is if we go here and hold down the spacebar, you can see that it's rotating, it's now translating. And if we hold down, press the A key, everything goes back to 0. So this is a little bit different as well, because the random number is being generated when the animator is being created. That's what the back quote and the comma do. You need to look that up. It's the same thing we use for macros, basically. So this creates a list, association list, but it actually evaluates this expression here. So when the animator gets created, it has a random value between 0 and 0.05. But that value is not random every frame. It's random per animator. That's why when we do the animation, so let's go back and do this a little bit less strongly. So if I hold down the space key, each square has its own random displacement that's the same for every frame. And since it's a translate by, it accumulates over time, and therefore they move. Hit the A key, and everything comes back to 0. Now, a lot of animation in computer graphics is done using what's called keyframe interpolation. So the animator might set values for angles or values for translations at a certain frame, say frame 10, and then at frame 20. And in between, the computer will interpolate the results and create animation for the missing 9 frames. So what we do here is basically, if we do that with our animators, the way things are right now. So let's say we take this square, and we want to create an animator for it. Now, we want a start position and an end position. So bottom left to top right. And we have a start frame 0 and an end frame 60. And we're going to set the animator of the scene to be one animator for that shape. And the initialization function just says translate to the start position. That's all it does. But then the update function sets the translation of the shape to be the smooth interpolation. This is one of those helper functions that we defined earlier. That takes a value between 0 and 1 based on the start frame and the end frame and the current frame, where we are in that range, between 0 at the start frame and 1 at the end frame. And then takes the animation data from the start and end positions and interpolates between those two. So it's a little bit convoluted perhaps, but let's have a look at it. And then we store the data here in the animator so it has access to it in its update and function. So let's just compile this and run it. So if I hit the A key, it goes down to -0.5, -0.5, which is the start position. And if I hold down the space bar, it moves up to the end position, which is 0.5, 0.5. And it does so in a smooth way over 60 frames. So if you pay attention, it starts off slowly, accelerates, and then decelerates at the end. So if we do it again, hit the A key, hold down the space bar, starts off slowly, accelerates, and decelerates. That's what the p-smooth-lerp does with that cubic function that we defined. I'm not going to get into the math of it right now, but actually I will in a little bit. But so if we have a straightforward non-smooth lerp function, define that as our animator. So here it'll have a constant speed from the beginning to the end. So it'll have an abrupt acceleration and abrupt deceleration at the end. So it's just a constant speed all the way along, and then when it ends, it just kind of goes thunk and stops. Whereas previously, it would accelerate slowly and then decelerate slowly, which is usually more visually pleasing in animation. So what is this smooth lerp thing that I'm talking about, this cubic shape? So let's look at this cubic shape as, cubic curve, as a shape. So if I generate that shape curve and display it as a polygon shape, this is what it looks like. So this is the point 0, 0. This is the point 1, 1. And if this was a straight line, it would give us a straight interpolation, which is what p-lerp does. And you have a jarring start and then a thunk, it ends. Whereas here, you can see it's kind of gradually ramps up, has a constant velocity towards the middle, and then ramps down and slows down. So this is the kind of ease in, ease out that's referred to in animation. And it's a principle that goes back to the old days of hand-drawn animation and Disney and Warner Brothers and so on. Almost every motion in nature does ease in and ease out. It's very jarring if you see things moving with sudden acceleration and deceleration. In fact, they look, for lack of a better word, robotic, like robots. All right. So we've defined this keyframe animator idea here. And this particular case takes these values and it happens to do a translation. But we want to do the same thing for rotations and the same thing for scales. So we write a macro that generates a keyframe animator for us instead of having to write each one separately. So what we do is basically, let's look at how we use this animator and then talk about it. We say define keyframe animator, translate, rotate, and scale. And that's the only thing we have to give it. Because the structure is exactly the same. The only difference is the operator. What is it doing? Is it doing a translate by, or rotate by, or a scale by? So let's just define this. And let's have a look at this. Let's not get scared by this macro expansion of what the animator is actually doing. So it's actually pretty straightforward. So we did the translate one. So this is define make translate animator. It takes the shape, the start and end values, the start and end frames, and then whether the interpolation should be smooth or linear. So it makes an instance of animator. The shape is passed in by shape. The initialization function simply says do a translate to the shape of the animator to the start value. The update function does the same thing we did before. It translates to, and then if we do a fun call to get the interpolation function, and if the interpolation was smooth, it returns a smooth lerp. If not, returns regular lerp. And then we call that on the tween, which gives us the parameter value between 0 and 1, and the animation data from the start value to the end value. And this is just a bunch of nested lists that store the start value, end value, start frame, end frame for us. So the thing to realize is that if this was rotate, the only difference is that this is called rotate animator, and down here it does a rotate to, and over here it does a rotate to. Otherwise, it's exactly the same boilerplate, the same structure as the translate keyframe creator. And that's why we decided to make this a macro, because we have for translate, rotate, and scale, we have the exact same things happening, and it's kind of wasteful to write all that stuff by hand and error prone. So all we do is we just define these three functions: make translate, make rotate animator, and make scale animator. And now let's see how we can use these. So if we define a shape, wrong key again. So there's our little cube, I'm used to 3D, our little square. So let's clear the animators in the scene and basically add a translate animator, a rotate animator, and a scale animator. And they all go between 0 and 60 frames, so it's the same thing. They all do smooth interpolation. The translate goes from -0.5 to +0.5. The rotate goes from 0 degrees to 90 degrees. And the scale goes from 1.1, which is the basic square, to a stretched out, thin shape. So if we do that, if you hit the A key to see where the initialization is, it's down there. And now if I hold down the space bar, it does the translation that we're used to, but it also does a rotation and a scale. A again, space bar. So that's a combined scale, rotate, and translate animation. Now, if you do the exact same thing here, exact same thing here, except we use linear interpolation instead of smooth interpolation. Hit the A key, hold down the space bar. So now there will be no acceleration, deceleration. It will just be a constant velocity, constant rotation, constant scale. And when it gets to the end, it just kind of goes thunk and stops. So that's linear interpolation. And it's not as pleasing as smooth interpolation, but obviously depends on what your animation is. If you are doing a robot and you want it to look like a robot and kind of be very mechanical and start and stop jerkily, you'll use linear interpolation. Otherwise, you use smooth interpolation. So let's do one more example here with the robot arm that we used earlier when we were talking about transformations and hierarchies. So we're going to add names slots to our shapes, so we can actually find particular shapes in a hierarchy, which we haven't been able to do up to now. So we'll compile that. And now we're going to create the same robot arm that we did before, if you remember. So this is all the exact same code as before. It's just like we created a bunch of wrist shapes and so on and so forth, put them in a hierarchy, and assign them starting values to look like a robot arm. So if we do that, we have the same robot arm. Should look familiar from last time that we did. But now we're going to assign some names to these guys. So we're going to take these global variables and assign names to them. So now that we're able to, if we do that, they have names. And what we can then do is do hierarchy when we add the animators. And we only do the add animator if the name is equal to the name of the object. So we can now selectively set animators for particular objects by specifying them by name. So this just does the rotate animator only, no translator scale. So it's the same rotate animator that we saw before with our square. Takes a shape, start angle, end angle, start frame, end frame, and we're having it do smooth interpolation for us. So we call this animate part rotation. So compile that. And then to do a flex animation, we're going to define a combined animation called flex animation over a number of frames. Clear the animators, and basically add the animators. This is the root node of the hierarchy. So the object shoulder goes from 0 to minus 60 degrees. Elbow goes from 0 to 120 degrees. Wrist goes from 0 to 90 degrees. And waist goes from 0 to 20 degrees, minus 20 degrees. So we create this function. And now, if we basically say we want this animation over 100 frames, we run this, and then we come over here and press the spacebar. It jumped a little bit because I think I didn't hit the A key for the, so now there we go, that's correct. That's over 100 frames. If I want it faster, over say 50 frames, initialize, hit spacebar, it goes twice as fast. But you can still see, hopefully, that it is accelerating and decelerating. So it's a smooth motion, right? So you start here, it speeds up, and then it slows down. And that might be more visible if we do it fast over 10 frames. So even over 10 frames, you can still see, you can feel the acceleration, deceleration. Starts slowly and ends faster. If we want to, we can see what this looks like with linear interpolation. So if I define that, let's do the 50 frame version. So you can see it mostly at the end, it's more noticeable. When it comes to a stop, it's a very jarring stop. And if I do the 10 frame version, which is pretty fast, so you can see it's kind of mechanical and comes to a jarring stop. So that's, let's put that back to smooth. That's animation with hierarchies. And that's the very basics of how all character animation is done in computer graphics these days. Whether it's, you know, the Transformers guys, it's just a more elaborate version of the same ideas. They'll have hundreds or thousands of parts and very, very complex hierarchies. But at the end of the day, each of those hierarchical pieces is being rotated around an axis over time. And that's how the animation is done. All right, thank you.